This is MT131, which is also sometimes M131 course, Discrete Mathematics. And this is our first tutorial. The course is in Discrete Mathematics. We will cover many topics, but the main goals for the course, first of all, logic means reasoning, mathematical reasoning, logic, inference, and proof. We will not do any proofs, but we will cover some topics from logic and inference. Second topic will be combinatorial analysis, which is counting, and probability. Those two topics are related. To calculate probability, you use some counting techniques, which we will study, and also we will study some basic principles of probability. The third major goal here is to study discrete structures such as sets, functions, relations, and graphs. You may be familiar with all this, but for functions we will use a different definition for functions. We will define functions using sets. These are the different chapters we'll cover. The details and the chapter numbers are all in the course calendar, which you can find in the LMS for the MT131 course. First chapter is logic, mathematical logic. Second chapter is sets, functions, and matrices. Chapter 4 is number theory and cryptography. Chapter 6 is counting. Chapter 7 is discrete probability. Chapter 8, I think, relations. And the final chapter we'll cover is about graphs. The first chapter is the foundation of logic. We will cover some basic principles of mathematical logic. Mathematical logic is a tool for working with compound statements. Compound statements here could be mathematical expressions, theorems, any statements that's written using mathematical methods. Many times in mathematics we want to prove that a statement is correct or not. You could use mathematical logic to do that. Basically, you use mathematical logic for working with compound statements. Logic, of course, is a big field, but we will mostly do mathematical logic. Logic is a study of correct reasoning, and this is applied to many disciplines other than mathematics. Here are the two major uses that concerns us. Logic is used in mathematics mainly to prove theorems. In computer science, when you write programs, programs supposed to accomplish something or do something, but you could use logic to make sure your steps are correct. But you can use logic to prove that the program will do what they are supposed to do. There is two types of logic. We start by looking at propositional logics, which deals with propositions. Propositions, we will define what a proposition is, are simple statements that can be either true or false. For working with proposition, this is the part where we study propositional logic. Later on, we will look at predicate logic. Predicates, of course, are statements with a variable that might cover a large set. This is another type which we will consider toward the end of the chapter. Predicate logic deals with predicates. The first definition of the book, the idea of a proposition, is what we will work with in this chapter. A proposition, and we usually give proposition names. We can denote them by P, Q, or R. A proposition is a declarative statement, and it tells you something. A declarative statement that's either true or false. If the statement or if the proposition is true, we write capital T for short, If it is false, we use capital F to denote that it is false. A proposition then is a declarative statement that's either true or false, cannot be both true and false, or in between. You have to be able to decide whether the statement is true or false. If you cannot do that, then you don't have a proposition. Not every statement is a proposition. Clearly, you need to exclude commands. Any statement in the form of a command or in form of a question, these are not proposition because they will not have a truth value. You cannot decide whether the statement is true or false. Here are examples of propositions, and also we'll look at examples of statements that are not proposition. The first example, Washington, D.C. is the capital of USA. This is a proposition. The truth value for the proposition is true. Second example, California is adjacent to New York. This is an example of a proposition. In this case, the truth value is false. Third statement is a mathematical equation, 1 plus 2 equals 3. This is a proposition that is true. If I write 1 plus 2 equals 5, this will be a proposition with a false truth values. Here are examples of statements that are not propositions. What time is it? That's a question. That's not a proposition. A second statement is meaningless. A third statement, read this carefully. This is a command. But in all these cases, these are not propositions. If you write 1 plus 2, and that's it, this is not an expression with a truth value. You cannot tell. This is different than 1 plus 2 equals 3. If you just write 1 plus 2, this is an expression with a non-true or false value, and therefore it's not a proposition. The final example, 1 plus 2 equal x, this is an expression with an unknown value of x. Because I don't know what the value of x is, then you cannot assign a truth value, and therefore this is not a proposition. In fact, this will be an example of a predicate. Once you know the value of x, you will have a proposition. But if we just write this statement as it is, this is an expression with an unknown value for x, and therefore it is not a proposition. Now, most of the time we work, simple statements or proposition are not enough to work with statements. We normally work with compound statements. What are compound statements? Compound statements consist of two or more proposition, two or more simple statements that are connected using an operator. What is an operator or a connective? This combines one or more operand, because an operator can operate on one statement, but it could also operate in more than one statement. Then the operator takes one or two or more statements or expressions and connects them together to make a larger expression or a compound statement. This is similar to what we do in arithmetic. In arithmetic we deal with numbers, but we have operations such as addition, and you take two numbers and add them, you get another number. For a logical statement, you use operators to take simple statements and form a more complicated expression or a compound statement. There is basically two types of operators. There's unary operators, which means they operate on one statement, on one thing only. The second type is binary operator. It takes two operand and connects them into a compound statement. Propositional or Boolean operators operate on the proposition, or basically you are looking at the truth values of these proposition. The Boolean operators or propositional operators work on the proposition or their truth values. Here is a list from your book of the operators that we will use. But these are not the only operators that are used in logic. Depending on the applications and in other fields of science, there may be other operators, but these are the ones we will look at. And we will look at each one of them in detail and give examples how to use it. The only operation here that is unary is the negation operation. All the others are binary. Unary, that means it will affect one statement or one object. Binary, which is all the operators except the first one, that means you start with two statements, use the operator to form a compound statement. The first operation is the negation. The short name for it is not. This is a unary operator, and this is the symbol we use for the operation is this symbol. The next operator is the conjunction operator. The short name is and. This is a binary operation, and the symbol for it is like the number 8 in Arabic. The next one is disjunction operator. Short name is or. This is a binary operation, and the symbol we use for it is similar to the number 7 in Arabic. Next is the exclusive or. We say XOR for short, a binary operation. The symbol for it is what you see here. This is like a circle with a plus sign inside it. Next operation is implication operator. The short name is implies. This is a binary operation, and we use an arrow. When you need two statements, so you start with a statement P, then you do the arrow, then Q. That forms the statement, the implication statement. P implies Q. The final operation or operator is a biconditional operator. The short name is IFF. This stands for if and only if. It is a binary operation, and you use a double-sided arrow. Yani the arrow goes in both directions. We will look at each one of these in detail, give examples how it is used. The first one was the negation operation. This is a unary operation. We need only one proposition. If you start with a proposition P, then not P, and you write P in front of it, use the symbol for negation. But this is read not P. This is the negation of the statement. But this is another proposition, which is the negation of the statement P. The negation, you can also read it not P. It is not the case that P. The short way to do this is just say not P. This is a negation of P. Here is a quick example. P is the statement London is a city. The negation, not P, is the statement London is not a city. In the English language, in most languages, you could there may be more than one statement that gives you the same meaning, so you can write the negation in this form. It is not the case that London is a city. The first form is enough to write the negation. P is the statement London is a city. The negation, not P, the London is not a city. And here is now our first truth table. Now you remember we started with a proposition P that is either true or false. Now we form the negation. But what about the truth values of the negation? To summarize the possibilities here, we have to list all the possibility for truth value of P and not P. This is called the truth table. For the negation, it's a simple table. In the table, again, we use capital T to mean true and capital F to mean false. This symbol with three lines above each other, it could be used to say in defined. Capital T defines true, and capital F defines or is equivalent to false. Here is the truth table. You notice that you have two propositions now, P and not P. The negation of P. P can either be false or true. if a proposition is false, then the negation will be true. If the proposition is true, then the negation will be false. يعني each row will give you a possibility. Either P is false and therefore its negation is true, or P is true and its negation will be false. This is called the truth table. We will use them for operators to summarize the truth values. We'll also use them to find truth values for compound statements. يعني we will see more truth tables. This is a simple truth table because we only are working with one proposition, a unary operation. طبعا the truth table will يعني can get more complicated. They may have more rows and more columns. But we will يعني see more examples of truth tables. The next operation is the conjunction operator, or AND. All the operators that we will do now are binary. You start with P and Q are proposition. Now you form P and Q. This is a compound statement, P and Q. Use the symbol for AND. You can write it using symbols as P, but then use the symbol for AND, then Q. This is read P and Q. This is called the conjunction of P and Q. Let's look at an example and then look at the truth table for that operation. The example here, P is the statement, I will have salad for lunch. The second statement, Q, is I will have steak for dinner. Now we use the AND to combine the two statements. P and Q is the compound statement, I will have salad for lunch and I will have steak for dinner. Here, طبعا the operation and combine the two proposition into one compound statement. Now you are working with an operator, a binary operator, so you are starting with two propositions, P and Q, and you want the truth values for P and Q. Now you have more possibilities. طبعا each proposition is either true or false, but we are looking at the truth values for the two propositions together. Here are the four possibilities. Both are false, FF, or P is false and Q is true, or P is true and Q is false, or P is true and Q is true. These are all the possible possibilities for the truth values of P and Q. Now, going back to the statement, when you say P and Q, for that to be true, both parts, both P and Q, must be true. The truth table, now to write the truth value for P and Q, if the statement are both false, you get a false truth value for P and Q. If one of them is false, such as in the second line, F and T, and the third line, T and F, the truth value for AND will be false. The only case where the AND operation will give you a truth statement if both P and Q are true. This truth table is easy to remember. The AND operation is always false except when both P and Q are true. Next operation is the disjunction, or we use OR. Again, you need two propositions, P and Q. The compound statement now is P or Q, or you can use the symbol for OR and write it as P or Q. This is called the disjunction of P and Q. But as we did before, let's look at an example and then we'll go back and see the truth table. P, the statement P is my car has a bad engine. Q is the statement my car has a bad carburetor. We use the OR to join the two. This statement is a compound statement, P or Q. Either my car has a bad engine or my car has a bad carburetor. طبعا the statement will still be accurate if you don't use either, if you just say my car has a bad engine or my car has a bad carburetor. This is still correct, but طبعا in English normally if there's a choice we use the word either. But here is the conjunction. Now with this type of statement, for the statement to be correct, since you said P or Q, for the compound statement P or Q to be true, only one of them needs to be true. One of the proposition needs to be true. In fact, it's only false, the only case where it is false if both of them happens to be false. But here is the truth table. For F or F will give you a false statement for P or Q. F or T is true. T or F is true. T or T is true. The disjunction or the OR operation is true in all cases except if both proposition is false. Later on we'll need this. We sometimes call the OR, this OR, we call it inclusive OR, because it allows for the possibility that both statements are true. Yani if both P and Q are true, then P or Q is also true. This is included, this is to distinguish it from the next operation, which is the XOR, which does not allow for both propositions to be true at the same time. But for now, the OR, the regular OR, yani will be true in all cases except if both propositions are false. And so far we worked with either unary operation, you work on one proposition, or two for binary operations. There is nothing wrong with combining and using more than one operation to formulate a more complicated statement. Starting with P, Q, R, and S, all of these are simple statements or propositions. There's all kind of ways you can form compound statements. Here is several examples. P or Q and R. You notice we use parentheses, and that means you take P and Q together and you apply the OR operation first. P or Q is taken together, then and R. Next operation, P or Q and R. This is almost exactly like the previous one, except the parentheses are, you take Q and R together. We will talk about parentheses later, but both of these statements use three propositions and two different operations to form compound statements. The third statement, not P or not Q, that uses two operations, the negation and the and it uses two propositions. Here is another one, P or Q and not R or S. The parentheses tell us take P or Q together as one statement, a sub-expression, and take not R or S as one expression. There's of course many other ways to form compound statements using any combination of operations and propositions. So far we looked at truth tables. We used them to summarize truth values for operators. We also use them to summarize truth values for compound statements. We started with the truth table for the negation, and we had the truth table had 2 rows. When we did the truth tables for binary operations, we had 4 rows, the number of rows doubled. Every time you double, every time you increase the number of propositions, you are doubling the number of rows. So on 3 proposition P, Q, and R, the number of rows will be 2 to the 3. Every time you add 1 proposition, you multiply by 2. 3 proposition, the number of rows is 2 to the 3, which is equal to 8. You should expect 8 because there is 8 different possibilities for the truth values for the 3 proposition. Okay, the end goal is to write the truth value or the truth values for the compound statement. And that will let you know when the statement will be true and when it will be false. So the first thing to do is you need a column for each variable, a column for P, a column for Q, and a column for R. Then you need a column for the sub-expressions, P or Q, and then finally you can go ahead and write the truth values for the entire statement. Now, with 3 propositions, here is the reason why there is 8 possibilities. Starting with just 2 propositions, let's just say Q and R, there is 4 possibilities, FF, FT, TT, and TT. TF and TT, 4 different possibilities. When you introduce a 3rd proposition, this proposition is either true or false. So if you start by assuming that P is false, there is 4 possibilities for Q and R, so there's 4 combinations. Now assume that P is true, and you still have 4 more possibilities for Q and R. Then altogether you have 8 different possibilities. You can easily check to see that all of these rows are different. They only need to be different by 1 value. Certainly all of these possibilities are different, and they cover all the possibilities for truth values. Now what you need to do is form P or Q, which is the first and second value. So it's easy to just apply the OR for the first and second row, and these are the truth values that you get. Finally, the entire statement P or Q and R is just applying the AND between the truth values of R, the column for R, and the column for P or Q. You should easily and quickly fill those values. You can see in this statement is sometimes false and sometimes is true. The table will tell you exactly when the statement will be true and when the statement will be false. The next operation is the exclusive OR. We already looked at the OR. This is different. This is called the exclusive OR. And the only difference is that this operation does not allow for both P and Q to be true, as we will see. It is exclusive. The symbol for it is the circle with the plus sign inside it. For short, we say XOR. And if you have 2 propositions, P and Q, you say P XOR Q. That means you're using the exclusive OR. This is called the X-junction operation. As I said, it is different than the OR that we looked at before, and it's used with 2 statements that cannot possibly be true at the same time. Here is an example. If P equals, or P is the statement, I will earn an A in this course. Q is the statement, I will drop this course. Drop this course meaning I will withdraw from the course. Clearly those 2 statements cannot be true. You cannot drop the course and still get an A for it, and you cannot get an A if you already dropped the course. But those 2 statements cannot be true together. You can use the XOR with that. P XOR Q says I will either earn an A in this course or I will drop it. Notice we used OR, but the meaning is exclusive. But you still use the word OR in English. In symbol you have to use the XOR. In the language you could use OR, but this is the exclusive OR in this case. And the meaning will tell you whether you have the OR or you have the exclusive OR. This is just to make sure we understand. And you either will earn an A or drop the course, but not both. You cannot do both. You cannot earn an A and drop the course at the same time. This operation is called exclusive OR. Remember the previous one we called it inclusive OR. This one is exclusive OR because it excludes the possibility that both P and Q are true. The truth table for this operation, the choices for P and Q are the same. Now this statement is true only if one of them is true and one of them is false. If both are false, then P, X, or Q is false. If both are true, the statement will also be false. The only time when this statement, or you're saying X or, you're saying either one of them but not both. This statement is true only if one is false and the other one is true. And for example, F, X or T is true. T, X or F is true. That's the second and third line is where the statement will be true because they have different truth values. If they have the same truth values, any false and false, or true and true, the X junction will be a false statement. Here are examples that we can tell the difference between the inclusive and the exclusive OR, because using the English language we use OR for both, for inclusive and exclusive. Normally the context of the statements will clarify whether we mean inclusive or exclusive. The first two propositions, Pat is a singer or Pat is a writer. When Pat is the name of a person, the same person can be both a singer and a writer, so we could use inclusive OR. But in this case, the meaning will tell us that you can use inclusive OR. The next two statements, Pat is a man or Pat is a woman. Of course, the same person cannot be both a man and a woman, so you should use exclusive OR. You need context to disambiguate the meaning or to clarify the meaning. For this class, assume OR to mean inclusive. Here are some exercises. This is to review the statements or the operation that we have covered so far. The three statements we'll be working with. P is the statement, it rained last night. Q is the statement, the sprinklers came on last night. R is the statement, the grass was wet this morning. Translate each of the following into English, meaning take a statement written in symbols, logical symbols, and write the English equivalent for that. Write the statement using an English sentence. Not P is the negation of P, so it should be, it did not rain last night. Not P is the negation of P, it did not rain last night. The next statement, R and not P, the R is the grass was wet this morning, and not P, it did not rain last night. R and not P is the statement, the grass was wet this morning, and it did not rain last night. The third statement, not R or P or Q. Not R is just the grass was not wet this morning, or it rained last night, or the sprinklers came on last night. So we will do this from time to time. We can either take English statements and write them in symbols using logical symbols, or take logical symbols and write them into English statements. That's what we mean by translating into English. Next, we'd like to discuss using parentheses. We already saw an example where you have a statement and part of the statement is enclosed in parentheses. These are called sub-expression. You're taking part of the expression. And the reason why you may want to do this, it would make the statement more clear. Which operation do you apply first? But here's an example that would demonstrate using parentheses. I just saw my old friend. This is F. This is proposition F. And either he is grown. This is G. Or I have shrunk. And let's say the statements again. I just saw my old friend. That's F. And either he is grown. This is statement G. Or I have shrunk, which is statement S. The way to write this using parentheses is F and G or S. Now this is يعني the first operation we used in the statement is AND. And combines the first statement, I just saw my old friend, and whenever you use either, there should be an OR. That means the statement that comes after AND should be taken together. And that's why you have the parentheses for the second part, which is G or S. If you place the parentheses somewhere else, like if you do F and G together, that would certainly change the meaning. This would mean something else. If you don't use parentheses, it's not clear whether you take F and G first and then apply OR S, or take G and S and then apply AND. The parentheses just clarifies the meaning. You take anything within parentheses, take it as one statement, as one sub-expression. If parentheses are not used, you can still, there is by a convention, there's an agreement on a certain order that you can apply. Different operators have different priorities. The priorities that we know is that you take the negation comes first. Anytime you have a statement where parentheses is not used, you apply the negation first. It takes precedence over and or. Apply it first. And here is a partial order of the operation. Apply AND first, negation first, then and or have the same priority, then the implication and the biconditional. We will see an example. If the parentheses are not used, then apply the operation in that order. For example, we looked at examples where you have negation and other operations. But if you write not S and F, here the negation should be applied first, so the negation is applied to S only. If I apply the negation, not S, and then apply and F. If I want to write the negation for the entire statement, S and F, then I should enclose it in a parentheses. And if I write not, then S and F within parentheses, here we want the negation of S and F. If you write it without parentheses, then the negation should be applied first, applied to S, and then apply the AND. The next operation we will consider is the implication operator. The implication operator is a binary operation. You need two propositions P and Q, and the way to use it is write P, then arrow, then Q. The first part, P, is called the hypothesis. The second part, Q, is called the conclusion. And the way to read this compound statement that P implies Q. What that means, as a compound statement, you are saying if P is true, then Q is true. If the hypothesis is true, then the conclusion is true. Now the statement does not tell us what happens if P is not true. And if P is not true, then Q can still be true or false. And we will look at examples of implications. If P is the statement you get 100% on the final, Q is the statement you will get an A, then using implication to combine the two statements, P implies Q, says if you get 100% on the final, then you will get an A. The first statement, you get 100% on the final, the hypothesis, comes after if, the conclusion comes after then. You will get an A. Now what we said is that if P is true, then Q is true. If you get 100%, you will get an A. Now what happens if you don't get 100% on the final? If P is false, then Q can still be true or false, and you can still get an A or not. The implication statement does not tell us what happened if P is false. The only thing we know when we use the implication, that if P is true, then we know that Q is also true. If P is false, then Q can still be true or it can be false. Again, one more time, P implies Q. Tell us that if P is true, then Q is true. So when will the statement be false? The implication statement will be false in one case only. If P is true, but Q is not true. All the other possibilities will give you a true statement. The table will show that if both statements are false, if P is false and Q is false, then P implies Q is considered to be a true statement. If P is false and Q is true, then P implies Q is considered to be a true statement. Notice the first two lines, P is false. If P is false, Q can still be true or false. From both cases, it's considered to be a true statement. The third line gives us the only case where the implication is false. If P is true and Q is false, then P implies Q will be a false statement. Of course, if both are true, then P implies Q will be a true statement. The other comment here is that P implies Q does not require that P or Q are ever true. We are only making a statement about the truth values. P implies Q tells you, and if P happens to be true, then Q is also true. That doesn't tell me that P or Q is true. It just tells me what happens if one is true. If P is true, then the conclusion that Q also must be true. The other thing that we need to know, and P and Q may not be related, as this example shows. 1 equals 0 implies that pigs can fly. If 1 equals 0, then pigs can fly. 1 equals 0 is a mathematical equation. Pigs can fly is a statement. Both happens to be false, and we said false implies false is a true statement. So from the logical point of view, even P and Q are not related, but comparing the truth values, false implies false will be a true statement. Here is the table. As you can see, if both are false, then P implies Q is true. If P is false and Q is true, then P implies Q is true. The third line is the only case where the statement is false. True implies false is a false statement. And of course, if both are true, true implies true will be a true statement. Here is a restatement of the same fact. In the implication statement, P implies Q, there does not need to be any connection between the antecedent, which is the assumption, or P, or the consequent. The consequent here is the conclusion, or Q. P and Q need not to be connected. We're only working with the truth values. The meaning of P implies Q depends only on the truth values of P and Q. Here are examples of using the implication. If this lecture ever ends, then the sun will rise tomorrow. This lecture will end, so this is true. The sun will rise tomorrow, so this is true. True implies true will be a true statement. Next example, if Tuesday is a day of the week, then I'm a penguin. Tuesday is a day of the week, this is true. I'm a penguin is false. True implies false will be a false statement. The third example, if 1 plus 1 equals 6, then Trump is the president of the USA. 1 plus 1 equals 6 is a false statement. Trump is the president of the USA is true, so this is false, implies true, so it should be a true statement. There are different ways of expressing the implication. Using logical statements, there's only one way, you just write P implies Q. But using, in the English language, there are many other ways to state the implication. All these statements give you the same implication, P implies Q. you can write if P, then comma, then Q. If P, comma, Q, and you don't use the then. Q unless not P. Q if P. Notice in this form, the assumption comes after the word if. Q will be true if P is true. There is also P implies Q. That's the most common way. P only if Q. Yani if P is true, then necessarily, or yani that will implies in Q is also true. Q when P, Q whenever P. Here is one way to do it. This is used in mathematical statements. P is sufficient for Q. Q follows from P. Q is necessary for P. A necessary condition for P is Q. A sufficient condition for Q is P. All of these forms tells you the same thing, and the P implies Q. We will look at examples, English sentences that gives you the implication in different ways. Here are examples. The original statement: if Maria learns discrete mathematics, then she will find a job. So if P, then Q. Another way to say that, same implication: Maria will find a good job if she learns discrete mathematics. This is Q if P. Or you could say Maria will find a good job when she learns discrete mathematics, or you could use whenever. But this is the form Q when P. For Maria to get a good job, it is sufficient for her to learn discrete mathematics. This is saying that P is a sufficient condition for Q. Maria will find a good job unless she does not learn discrete mathematics. In this form, you have Q unless not P. But there are many ways to say the implication. There are more examples in your book that you can look at of different ways of using the implication statements when you use English sentences. Here is a truth table for a statement that has the implication P or not Q implies P and Q. Notice now the assumption is a statement. We use parentheses. That means you take P or not Q. That's the assumption. The conclusion is also a compound statement, P and Q. The truth table is done similar to what we did before. You have only two variables, P and Q. There is only 4 rows in the truth table. We need a column for P, a column for Q, a column for not Q. Then for this sub-expression, P or not Q, we need a column. Also for P and Q, you should have a column. And then your compound statement is actually, you are taking the column for P or not Q, implies the next column, which is P and Q. Here, for this last statement, true implies false is false, false implies false is true, true implies false is false, and true implies true is true. This last column is the truth value for the compound statement we started with. This is a statement that uses the implication. Now we would like to talk about logical equivalence, and here is the first case where we will see an example of logical equivalence. First of all, logical equivalence, what does that mean? In this example, we want to show not P or Q is logically equivalent to the statement P implies Q. Logical equivalence means the two statements have the same truth values. Whenever one is true, the other one will be true. Whenever one is false, the other one is false. They have exactly the same truth values, but we say that they are logically equivalent. طبعا one way to show two statements are logically equivalent is by doing a truth table and having one column for each statement and compare the truth values. If they are the same, then the two statements are logically equivalent. If they differ even in one value, the statements are not logically equivalent. But here is the truth table. طبعا here you could use طبعا an extra column for not P. But here are the truth value for not P. This is the third column, not P or Q. And the last column, the fourth column, has the truth values for P implies Q. So you notice that when the first one is true, the other one is true. You have true, 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 false, false, true, true. So they have exactly the same truth values. So we will say they are logically equivalent. There is another way to prove logical equivalent using logic laws, but certainly you can always use a table to show that two statements are logically equivalent by showing that they have the same truth values. Before we move to logical equivalence and see examples of proving logical equivalence for some statements, we are still with the implication statement. Using the implication statement, you can define new statements, the converse, inverse, and contrapositive. The starting point is the implication statement, P implies Q. The converse of the statement is Q implies P. You notice the conclusion becomes assumption and the assumption becomes conclusion. For P implies Q, the converse of that statement is Q implies P. The inverse is not P implies not Q. Starting with the statement P implies Q, if you apply the negation to each one of them, it becomes not P implies not Q, and this is called the inverse of the statement. The contrapositive, you have to apply the negation and also change the order. For the contrapositive is not Q implies not P. So let me repeat those three and then we will look at an example. The original statement is P implies Q. The converse is Q implies P. The inverse is not P implies not Q. And the contrapositive is not Q implies not P. Let's look at an example of forming the converse, inverse, and contrapositive for an implication statement. The statement here is, we want to write the converse, inverse, and contrapositive for the following statement. If x doesn't equal 0, then John is a programmer. For the first statement, P is x doesn't equal 0. This is the assumption. The conclusion, Q, John is a programmer. The converse will be, if John is a programmer, then x doesn't equal 0. Q implies P. The inverse, we have to apply the negation, but the negation of x doesn't equal 0 and x is equal to 0. And the negation of John is a programmer and John is not a programmer. The inverse will be, if x is equal to 0, then John is not a programmer. Contrapositive, not Q implies not P. If John is not a programmer, then x is equal to 0. And here is an important note, in that the negation operator is different from the inverse. The way to write the inverse for P implies Q is not P implies not Q. Not P implies not Q is the inverse of P implies Q. This is not the negation. We will see how to write the negation for the implication, but the negation operation, not P implies not Q, does not give you the inverse. Not P implies not Q is the inverse. It's not the same thing as the negation. We will see the negation, and after a few slides we will see how to write the negation of P implies Q. The last operation we will consider is the biconditional. Biconditional, the arrow goes in both directions. It is a binary operation. The way to write it in English, يعني أول شيء in symbols you use the double arrow. To write it in English you write P if and only if Q. Now if you remember the implication, P if Q will give you in Q implies P, and if you write P only if Q, that gives you P implies Q. But to use them together, if and only if, that means P implies Q and Q implies P. Yani the arrow goes in both directions. Another way to say that, you can say if P then Q and conversely. Yani P implies Q and the converse, Q implies P. Both are true. Yani each statement implies the other one. The other forms of implication we use sufficient and necessary. For P is sufficient and necessary for Q. This is used a lot in mathematics. If you say P is sufficient for Q, that gives you P implies Q. If you say P is necessary for Q, then that means Q implies P. If you use them together, then what you have is P implies Q and Q implies P, which is the biconditional. طبعا using symbols as we stated before, use P, use a double arrow, P, if and only if Q. The truth table, yani this statement will be true if both are true or if both are false. If they have the same truth value, the biconditional statement will be true. If they have different truth values, then the statement will be false. So here is the table. If both are false, P if and only if Q will be true statement. If one of them is false and the other one is true, like in the second and third line, the statement P if and only if Q will be a false statement. And finally, if both are true, then P if and only if Q will be a true statement. طبعا يعني this table is not hard to remember. يعني if P and Q have the same truth values, يعني both false or both true, the statement P if and only if Q will be true. If they have different truth values, and if one is true and one is false, the statement will be the double implication or biconditional will be a false statement. Here is more translation, English sentences into logical expression. Yani take an English statement, break it up into simple yani propositions, and write it using logical symbols. Here is an example. If you are a computer science major, that's the first statement. This is C. Or you are not a freshman. A freshman is a first year student. If not a freshman, that means you're second, third, fourth year student. If you are a computer science major, this is C. Or you are not a freshman, this is not F. Then what is the conclusion? You can access the internet from campus. And this statement is A. Here the assumption is a compound statement, and you should take the first two statements together, joined by or. Yani this is before then. The conclusion will be the statement, you can access the internet from campus. You can translate it this way: C or not F implies A. Notice we took C or not F together because this is a condition. This is the assumption. C, either you're a computer science major or you're not a freshman. That is the condition. The conclusion is A, which is you can access the internet from campus. And the other thing, we state every time you use parentheses, that will tell you which expressions you have to take together, which sub-expression. Best if parentheses are not used, then the order that you should apply is listed in this table. But anything within parentheses must be taken first. It has top precedence. The negation is next. And then in third place, there is three operations which have the same priority: and, or, XOR. In the fourth level, implication, and biconditional. If you have more than one operation that has the same priority, you should apply them from left to right. Here is more truth tables. We will just cover this quickly, but again here the problem here, he doesn't use parentheses. The person who prepared those slides. This P or Q implies not R. We do know that OR takes priority over implication. This operation OR should be applied first, so you take P and Q, P or Q together. And if you want to write parentheses, you should enclose P or Q in a parenthesis. That's the assumption. Implies the conclusion here is not R. Here is the truth table. You can check the details. But طبعا again, you now have 3 variables, P, Q, and R, so that you have 8 rows in the table. You need the column for each variable. You need to fill the truth values for the 3 variables in the way we did before. Then you need a column for not R. You need a column for the sub-expression, the assumption, P or Q, and then your final column will give you the truth value for the statement you started with. This is just the column for P or Q implies the column to the left, which is not R. This last value, the last column, gives you the truth values for the original statement. Here is an application of those operations. طبعا the operation we looked at is applied to truth values, true or false, but you can replace true by 1 and replace false by 0. The time that you do this, there is many applications where you have you are working with only zeros and ones. You can think of the 0 as false and 1 as true, and then apply the operations, logical operation, the AND, OR, XOR. First of all, you are working with bit strings. Bit strings meaning a sequence of numbers that has only zeros or 1. You can apply those operations on 2 strings. The 2 strings have the same number of digits. Each digit is either 0 or 1. And now each digit, if it's 0, then think of it as false. And if it is 1, think of it as true. Here is the result of applying AND. You apply it to each 2 digits that are in the same position. The first 2 digits from the 2 strings, the second 2 digits, third, until you finish, until you reach the last pair of digits. فالAND مثلا for the AND operation, take 0, this is the first digit from the first string, with 1, 0 and 1, so this is like false and true, so the result will be 0. Next column, take 1 and 1, this is like true and true, you get 1. 1 and 0 is 0. 0 and 0 is 0. You do this to every pair. These have the same length. Apply the operation for each pair of numbers. You should either get 0 or 1. This is the AND operation. The AND operation, to get 1, both of them have to be 1. If either one of them is 0, the result will be 0. For the OR, you get a different result. For the OR, it is enough that one of them is 1. If both are 0, you get 0. If one of them or both are 1s, you should get 1. Let's do few. 0 or 1 is 1. 1 or 1 is 1. 1 or 0 is 1. 0 or 0 is 0. You should do this for all the digits. The third line gives you the results of applying the XOR. For the XOR, of course, if both are 1s or both are 0s, the result will be 0. If one of them is 1 and the other one is 0, the result should be 1. Let's do a few. 0 XOR 1 is 1. 1 XOR 1 is 0. 1 XOR 0 is 1, 0 XOR 0 is 0. طبعا you should do this to each pair of digits. This is just an application. And later in the book you will see some applications where you end up with sequences of zeros and ones. It's very useful to be able to use the operations from logic on these bit strings. We will see other examples where applications where you can actually apply the logical operations to sequences of zeros and ones or bit strings. Returning back to propositional equivalence, just to remind you, two statements are logically equivalent if they have the same truth values. We have some definitions. A tautology is a compound proposition that's always true. For example, if we take P or not P, this statement is always true because either P is true or not P is true. But the compound statement P or not P is equivalent to a tautology. A contradiction, on the other hand, is a compound proposition that's always false. For example, P and not P is always false, so it's equivalent to a contradiction. Other compound propositions are contingencies. So a contingency then is a proposition that's sometimes true and sometimes is false. Here is an example of a tautology, and we will use a truth table to prove that it is a tautology. P implies P or Q. The truth table for this proposition shows that P implies P or Q is always true, and therefore it is a tautology. We have other equivalence laws. Most of these laws are easily proved using a truth table. Now these laws, you can consider them to be true and use them to prove other formulas, as we will do in the next slide. The laws that will be used, the first one is the identity. P and a tautology is equivalent to P. P or a contradiction is also equivalent to P. The domination law, P or a tautology is equivalent to a tautology. P and a contradiction is equivalent to a contradiction. The idempotent, P or P is equivalent to P. P and P is also equivalent to P. The double negation, not P is equivalent to P. Commutative laws, P or Q is equivalent to Q or P. P and Q is equivalent to Q and P. The associative laws, P or Q or R, take P with Q first, P or Q or R is equivalent to P or Q or R taken together. When you are applying the OR, you can take any two together first and then apply the third OR. You get the same result whichever order you take. In fact, you don't even need to use parentheses. You can just write P or Q or R. For the AND, you have a similar associative law. P and Q and R is equivalent to P and Q and R. You take the P and Q together first and then R, or take P and Q and R taken together. This is the associative law. The distributive law, you have two formulas. The OR operation distributes over the AND also the second law, the AND will distribute over the OR. The first formula, P or Q and R is equivalent to P or Q and P and or R. The second formula, the AND distributes over the OR, P and Q or R is equivalent to P and Q or P and R. De Morgan law we can use to write the negation for the AND statement and for the OR statement. The first De Morgan law, not P and Q is equivalent to not P or not Q. Notice here we apply the negation for each proposition, and the AND turns into OR. The second De Morgan law, we can write the negation for the OR operation. Not P or Q is equivalent to not P and not Q. Here the OR becomes and we apply the negation to each proposition. The tautology and contradiction examples we started with give us two more formulas. P or not P is equivalent to a tautology. P and not P is equivalent to a contradiction. Here are some implication rules, rules that involve implication and also the biconditional. The first statement we already proved using a truth table. P implies Q is equivalent to not P or Q. Notice in this formula you take the implication statement and write it in terms of negation and OR. So this is considered to be an important formula or rule. We already proved it using a truth table. The second formula tells us how to write the negation of the implication operation. Not P implies Q. You can replace P implies Q by not P or Q. This is true from the previous example. P implies Q is equivalent to not P or Q, so you can replace P implies Q by not P or Q. Now apply De Morgan law. Not P is equal to P, or becomes and, but then not Q. So this is the correct way to write the negation for P implies Q. The negation of P implies Q is equivalent to P and not Q. The next statement deals with the implication operator. P implies Q is equivalent to not Q implies not P. You should remember this as the contrapositive. What this formula tells me, every implication statement is equivalent to its contrapositive. The third or the next operation is a biconditional. P if and only if Q is equivalent to P implies Q and Q implies P. In fact, you could use this statement as a definition of the biconditional operation. The final formula shows us how to write the negation of the biconditional statement. Not P if and only if Q is equivalent to P XOR Q. Here is we already used a truth table to prove equivalence relations. You can also use logic clause to prove equivalence, the equivalence of two statements. We will do this for these two statements. We will prove that they're equivalent using a table and also using logic laws. So we want to show P or Q, that's the first statement, and not P and not Q are logically equivalent. One way to do this is using a table. If we do the table, you look at the column for P or Q and the column for not P and not Q. They are exactly the same. But the two statements have the same truth values and therefore they are equivalent. Now you can also use logic clause to prove the equivalence. If you start with the second statement, not P and not Q, apply De Morgan law, you get not P, which is just P, and becomes OR, and then you have not Q, which is Q. So applying De Morgan law, this statement becomes P or Q, which is the first statement. يعني you can prove the equivalence in this case using logic laws. Here is the truth values for the first statement, and here is the truth values for the second statement, which proves their equivalence. Here is another example of showing two statements are logically equivalent using logic laws. We want to show that not P or not P and Q is equivalent to not P and not Q. طبعا to use logic laws you must start with one statement and simplify it until you get to the second statement. Starting with the first statement, not P or not P and Q, apply De Morgan law to the OR. You get not P and, the OR becomes and, not the second part, which is not P and Q. This is applying De Morgan law to the OR. Now apply the negation to the and in the bracket, so you get not P, and becomes OR, but then not Q. In the next step, you have the double negation, not P can be written as P. Then you can apply the distributive law, يعني distribute the and over the OR. You get not P and P, or not P and not Q. This is the distributive law. Not P and P is just F, which is a contradiction, or not P and not Q. And then in the next step, anything or a contradiction gives you the same thing you started with. And this is bracket, or F gives you the same bracket. So the final result is not P and not Q, which is the second statement. So we started with the first statement, applied De Morgan law twice. We applied the double negation, the distributive law, the negation, and then the identity, and we end up with the second statement, and that proves that they are logically equivalent using logic laws. Here is a second example. I'll let you check the details, but you can use logic laws to prove something is a tautology, so you only have one statement here to prove a tautology or a contradiction. يعني here you only have one statement. You could show it's a contradiction, or if it happens to be a tautology, you can do يعني the same method to show it's a tautology. For this statement, it will end up being a contradiction, and the way to do this is to simplify the statement using the different laws. In the last step, you should get a contradiction. Here طبعا you are applying different laws. Every step you are getting an equivalent statement, and the last statement is F, a contradiction that proves that your original statement is a contradiction. Now the final topic in this chapter deals with predicates. طبعا we started discussing propositional logic, so we were working with propositions. Now we would like to define predicates and see how we can use them. طبعا with predicates you use quantifiers. This is يعني what we will do next. The definition of a predicate is any statement that has a variable. It may have one variable or more than one, but provided that once you determine the value of the variable, you get a proposition, and therefore you can decide whether the statement is true or false. Here is an example: x is greater than 3. You can write it طبعا using symbols. The statement is x greater than 3. This is طبعا a statement that depends on x. So P of x is a predicate. It depends on the variable x. The predicate statement is x is greater than 3. Now, if you don't determine the value of x, this is not a proposition, but with a predicate, once you define or once you determine the value of x, you can decide whether the statement is true or false. For example, for x equal 4, this is P of 4. This is a predicate evaluated at x equal 4. Now the statement becomes 4 is greater than 3, which is a true statement. If I let x equal 1, this is just P of 1, yani the predicate evaluated at 1 becomes the statement 1 is greater than 3, which is false. Here's an example of a predicate that has 3 variables. R of x, y, z is the statement x plus y equals z. Yani the first plus the second equals the third. So now to use the predicate, if you determine or if you evaluate the predicate at certain values of the variables, you should get a proposition and you can decide whether it's true or false. For example, R of 1, 2, 3, that means you must replace x by 1, y by 2, and z by 3. The statement becomes 1 plus 2 is equal to 3. And that is a true statement. Of course, the same predicate, Rx, y, z, is the statement x plus y equals z. All those 3 variables are integers, and you can decide what values you can use, which we will define later as the domain of the predicate. Now, suppose that all the variables here are integers. Then whenever you evaluate a predicate, and if you replace the variables by integers, the result is a proposition, so you can determine whether it's true or false. The first value, at x equal 2, y equal -1, and z is equal to 5, this is just 2 minus 1 equal 5. This is, of course, a false statement. The second one, R3, 4, 7, means 3 plus 4 equals 7. This is a true statement. The third statement, Rx3z, is not a proposition because the values of x and z are not determined. Here's a second predicate. The predicate Qxyz is the statement x minus y equals z. Now, if you evaluate it at 2 minus 3, 3, this is equivalent to saying 2 minus -1 equals 3, which is a true statement. If you evaluate it at 3, 4, 7, the statement becomes 3 minus 4 equals 7, which is false. The third case, here x and z are not determined, so this is not a proposition. Also, since with a predicate, if you replace the variable by a specific value, you have a proposition, so you can use the operations, the or, the and, the implication. You could use it with the predicate after you evaluate it at a given value. For example, P of x is the predicate x is greater than 0. You can determine the truth value of these statements. P of 3 or P of -1. This is true or false, which is true. P of 3 and P of -1 is true and false. That gives you a false value. P of 3 implies P of -1 is true implies false, which is false. P of 3 implies not P of -1 is true implies true, so this is a true statement. طبعا anytime the predicate there is a variable with undetermined value, you don't have a proposition and therefore you cannot determine the truth value. For example, P of 3 and P of y, here the y is not determined, so this is not a proposition, there is no truth values. Same for the statement P of x implies P of y. Since x and y are not determined, there is no truth value. Now with quantifiers, since a predicate involves variables, the values that you can substitute for the variable is called the universe of discourse or the domain. طبعا domain is shorter, we use domain most of the time. The domain is the values that you can substitute for the variable in a predicate. If you do this, then you can use quantification with predicate to determine or to state for which value is the predicate is true. Here there is two types of quantification. Universal quantification. This is when you say for all the values in the domain. The other one is the existential quantification. This is when we say that there exist values in the domain where the statement is true. So we will see those two quantification, and we will use them to make statements about the truth values of a predicate. طبعا in the language, in the English language, quantifiers can be used يعني to mean يعني they are used for certain statements to describe certain predicates. When you say all men are mortal, this is يعني here the domain is the set of all men, but this statement says all men are mortal. The second example is for existential quantification. You say some cats do not have fur. The quantification that we will use the universal quantifier, which means for all values in the domain. This is the symbol we use for it. It's like an inverted A, capital A. The existential quantifier, we are saying there exist, there is some values. The symbol for that is look like an E, the mirror image of E. This symbol, once used in front of the quantifier, you are saying there exist some values where the statement is true. Here is how we write it. You use a symbol for that represent for all. This is for all x p of x. That means that p of x, the statement, the predicate p of x, is true for all x in the domain. The existential quantifier, you write there exists an x such that p of x, that says p of x is true for some values in the domain. It could be even one value. It could be true for more than one value. The quantifiers are set to bind the variable. That means it specify the variables, the values for the variable where the statement is true. طبعا the domain, when you work with a predicate, the domain, it's important to know what the domain is, because a predicate can be true in one domain, but it could be false in another domain. For example, let's look at a predicate and see how it is true in one domain but not true in another domain. What if we write this statement here? The statement says for all x, x squared is greater than or equal to x. This statement will be true or false depending on the domain. If you take the domain to be the set of all real numbers, then this statement is not true. For a statement like this to be true, it must be true for every value. If your domain is a set of real numbers, you know it's not true for x equal 1/2. Then a 1/2 square is equal to 1/4, and 1/4 is not larger than or equal to 1/2. Anytime you have a statement like that and prove that it's false by giving an example where the statement is not true, this is called a counterexample. And there could be more than one counterexample, but to show the statement is false, you only need to show it is false for one value, which we call a counterexample. So this statement is not true if the domain is a set of real numbers. What happens if we take the domain to be the set of integers? Now the statement will be true. Then any integer, when you square it, you'll get a number larger than or equal the integer you started with. I hope this example shows in predicates. When you work with predicates, the domain must be known. Then the truth of the statement will depend on which domain you use. Here are some examples of existential quantification. There exists an x such that q of x means there exists an element x in the domain such that q of x is true. This statement will be false if you cannot find any element or any number in the domain that makes this statement is true. Here is an example. if Q of x is the statement x is equal to x plus 1, and the domain is the set of all real numbers. There is no real number such that you can add 1 to it and get the same number. But this statement is false for all x. For the quantification, there exists an x such that Q of x is a false claim. It is a false statement. Then there exists an x such that Q of x is false because there is no real number such that x is equal to x plus 1. In example 2, let's let Q of x equal x squared. Q of x is a statement x squared equal x. The domain is a set of real numbers. Now, if you say there exists an x such that Q of x, this is a true statement. All what you have to do to prove it's true, just find a value, even one value, where the statement is true. طبعا, if the domain is a set of real numbers, you can use x equal 1, 1 squared is equal to 1, or even use x equals 0. But this statement is true for some values, some real numbers, and therefore the statement there exists an x such that Q of x is a true statement. Of course, the same predicate can be used over a limited domain. For example, the same predicate we looked at just in the previous slide. P of x is the statement x squared is greater than or equal to x. The domain here is a limited set. The domain has the numbers 0.5, 1, 2, 3. Now, when you use the universal quantification, you can write it, since this is a limited number of values, you can evaluate the predicate at each value and use AND, because this says P of x is true for all x, so you can write P of 1/2 and P of 1 and P of 2 and P of 3. This says the same thing as for all x, P of x. We happen to know that P of 1/2 is false. The remaining values are true, but this is an AND operation. For the result of this statement will be false. This statement was false in the set of real number. It still will be false in any set that contains a counterexample. The statement is false for this limited set. Now, for the same domain, you can also write the existential quantification in a different way. There exists an x that says that P of x is true for some value. So either P of 1/2, the statement is true for 1/2, or P of 1, or P of 2, or P of 3. This is writing the same statement that exists an x such that P of x. P of 1/2 is false. The remaining values are true, but this is an OR operation, so the net result will be true. Okay, suppose now let's look at an example where you have two variables in a predicate that depends on two variables, and the domain for both x and y is the set 1, 2, 3. Again, you can write both existential and universal quantification in one statement. For example, here, remember now we started with a predicate that has two variables. So if you write there exists an x such that P of x, comma 2, you're saying 2 will be fixed. So you're only looking at the statements with x being a variable. If 2 stays fixed, and x runs over the value in the domain. For this statement, that exists an x such that P of x, comma 2 can be written as, just change the values of x. So this is P of 1, 2, or P of 2, 2, or P of 3, 2. Here the y is fixed at 2, and x takes the values in the domain, which is 1 or 2 or 3. In the second example here, x is fixed and y is variable. You can write for all y, P of 3y. Here x is fixed and y takes on the value 1, 2, 3, which are the values in the domain. This is for all, so you use AND. But this statement can be written as P of 3, 1 and P of 3, 2 and P of 3, 3. The x stays fixed at x equals 3. The y takes on the values 1, 2, and 3. طبعا use and because this is a universal quantification. Next, we would like to see how to write the negation of the universal quantification and the existential quantification. The first formula, if you want to write the negation for the universal quantification, before you apply the negation, for all x, P of x means P of x is true for all value. The negation should be that P of x is false for some value. So you can write this as there exists an x such that not P of x. Yani P of x is false for some value of x. For the existential quantification, without the negation, there exists an x such that Q of x means that Q of x is true for some value. So the negation should be Q of x is not true for any value. And that can be written as for all x, not Q of x. Here are examples of using the negation. P of x is the statement x squared minus 1 equals 0. The domain is a set of real numbers. Now, what is the truth value for all x, P of x? Well, actually, the statement is true only for x equal 1 and x equal minus 1. So the statement for all x, P of x is false. Now, what about the statement that exists an x such that P of x? This is true because the statement is true, for example, for x equal 1. It happens to also be true for x is equal to minus 1, but the statement that exists an x such that P of x is true. Now, what about the negation of these statements? The negation of the first statement, since this statement is false, the negation you should expect to be true. The negation of for all x, P of x is equivalent to there exists an x such that P of x is not true. This means x squared minus 1 does not equal 0. Is this statement true? Well, there is many values for x where x squared minus 1 doesn't equal 0. So this is a true statement. This is expected since this statement is the negation of the statement for all x, P of x, which happens to be false. The negation of a false statement will be true. Now, the second statement, there exists an x such that P of x is a true statement, so the negation should be false. The negation of that statement is that the statement is there exists an x such that P of x, the negation should be for all x, not P of x, not the x squared minus 1 does not equal 0. This is a false statement, and for example, if you use x equal 1, you will have x squared minus 1 will equal to 0. So this statement is false, which of course we expect that since this is a negation of a true statement. Here is more examples of working with universal quantification. Let P of x be the statement or the predicate x plus 3 equal 4x, where the domain is the set of integers. We want to determine the truth values of the statement for all x, P of x, and justify our answer. This statement actually is true for one value only, which is x equal 1. So the statement for all x, P of x is false. The justification for that, give a counter example. For example, if you use x equal 2, for example, 2 plus 3 is equal to 5, but 4x is equal to 8. So the statement is not true for x equal 2. Therefore, the statement for all x, P of x is false. But certainly x equal 2 will work as a counter example. Now we're back to translating. Again, when we work with quantifiers and logical statement, you can translate using predicates and quantifiers. So here are some examples. Every student in this class has studied math and C++ course. The universe of this course in this case is the all students in this class. So you can write this statement at every student, every means for all. So for all x, we know what x is. It is a student, and the domain is the set of all students. So for all x, and x is a student, m of x means the student have taken math and the student have taken C++ x, meaning the student have taken the course C++. For all student, all x, the x have taken math and taken C++. Let's see using the same, we'll use a different domain. Here is an example for every person x. Here now x could be any person. If x is a student in this class, then x has studied math and C++. The universe of this course here is all people, and x could be any person. So you can write this statement as, for all x, S of x, if x happens to be a student in this class, what is the conclusion? The conclusion, this implies that the student x has taken math and x has taken C++. This is again translating. You can translate English languages to logical statement, and you can of course do the reverse. If you have a logical statement, you can convert it into a sentence from the English language. Here are some examples for the existential quantification. Some student in this class has studied math and C++. The universe of this course is students in this class. Some students, that means there exists an X, such that there exists a student, such that the student has taken math and has taken C++. If you change the domain, if the domain is the set of all people, then the statement can be written, there exists an X, there is a person, such that the person is a student in this class, that's S of X, and has taken math and have taken the course C++. Now in summary, with the quantification, the universal quantification, if you say for all x p of x, that means p of x must be true for all values in the domain. It's not enough to show that p of x is true for some x, you need to show that it's true for all values in the domain, which is more difficult than proving it's false. To prove it's true, you must show it's true. You must prove that it's true for all values x in the domain. An equivalent statement, if you want to show for all x, p of x is true, you can show the negation of the statement is false, and you can show that the statement that exists in x such that not p of x is false. Then if the negation is false, then the original statement is true. Now to prove the statement for all x, p of x is false, this is easier because you only need to show it is false for one value. And we call this a counterexample. Anytime you want to show, if it happens to be false, you can prove that by just giving one example, a counterexample. Now for the existential quantification, it's easier to prove that it's true. When you claim there exists an x such that q of x, you only need to show the statement is true for even one value. It is enough to exhibit some x in the domain for where q of x is true. To prove it is false, if it happens to be false, it is not enough to show that q of x is false for some value. You need to show it is false for all values.